For problem statement 1, we have a time-dependent one-dimensional heat conduction through the thickness of a rocket metal casing. The inner surface of the casing is exposed to a hot combustion gases around 300 Kelvin. So the importance of this study is to prevent a catastrophic failure, to understand the thermal stress and fatigue of material, and to help selecting the best material. Why is implicit method is chosen for the one-dimensional time-dependent heat conduction? It is unconditionally stable for linear problems, no strict requirement on time step for stability, and more robust for especially for stiff problems or long-time simulations. So here's the governing equations. So here is the programming for the implicit method. We have the parameters, the casing thickness, density of wall, ambient temperature and specific heat, and also the thermal conductivity. So what the user need to is they need to input the number of spatial intervals, hot temperature in Kelvin, time step in seconds, and also the total simulation time in seconds. So then they will calculate the number of time step and also the fine grid for the error estimation. So next, for the implicit method function coding, so first we calculate the dimensionless parameter R, but unlike the explicit method, we do not need to make it less than 0.5 since the implicit method is very unconditionally stable. So they use the matrix formulation unlike explicit method. Okay, so next we need to solve the temperature, cause and fine using the formula above, and then we need to solve for the cause and fine grid, and then we need to interpolate the fine grid to cause grid so that we can use the data from there to find our approximate error. So then we display it in table the interval, position, the temperature for the cause and fine, and also the approximation error. And then we use all of this data to plot the graphs so we can see the difference between the cause and fine better. So what the user needs to input is the number of spatial intervals, time steps, the temperature of the hot combustion engine, and also the total simulation time. The outcome is the user is expected to have the result table and also the graph. So here is the simulation. The user will run the program and you need to input the number of spatial intervals and 5000 Kelvin for the temperature, 0.1 seconds for the time step, and 5 seconds for the simulations, total simulation time. So here is the temperature distribution comparison at t equals to 5 seconds. And this one is the table that we get from the coding. Yes. So here is the input that the user need to add in. So here is the graph and here is the result table so the user can compare. So based on the result achieved in the previous slide, we can see that this method can be made using the first order or second order accurate in time, suited for long-term simulation, stiff system, and probably with fine special grade. It has high efficiency for long-term simulation as fewer steps needed, and convergence improved with finer mesh and smaller time step. Effect of step size only affects the accuracy but not the stability. The programming difficulty is quite high because it required matrix to solve. And for the advantages is unconditional stability regardless of time step size, suitable for problems where fast and slow process coexist, and more accurate with current Nicholson method due to combining implicit with midpoint approximation. So for the limitations, it is higher programming complexity as it needs good handling of matrix for equation, less accurate for very large time steps, and a high computational cost per step compared to the explicit method. That is all from me. Thank you.